Now we continue on the material balance that involve the chemical reaction. Continue on the reaction that I did an example of the incompressed combustion of methane. If we talk about incompressed combustion, when you react with food with the oxygen or oxidation with oxygen, if the complete reaction or combustion, we have two products, the main two products, carbon dioxide and water. If the reaction gave the product as carbon monoxide, we call it is the incomplete reaction. For this case, methane is burned with oxygen, right? But oxygen is not pure oxygen. Oxygen is included in air. That's right. The methane is burned with air in a continuous state combustion. That's right. The continuous state combustion, that means we have feed and output, input and output continuously. Okay, we can assume the system is steady state. There's no the mass accumulate in the system like this. Okay, after the combustion, the yield are a mixture of carbon dioxide, carbon monoxide, and water. For this case, we have incomplete and complete combustion. We have two reactions occur simultaneously. The first reaction is methane oxidized by oxygen. That's like 1 mole methane oxidized by 1.5 mole oxygen. That's like to produce 1 mole carbon monoxide and 2 mole water. And the second reaction is methane can also oxidize with oxygen. 1 mole methane oxidized with 2 mole oxygen to produce 1 mole carbon dioxide and 2 mole water. These two reactions are balanced already. You can check the atom left-hand side and right-hand side is the same number of atoms. Right? For this case, the feed two reactor contain 7.8 mole percent methane, 19.4 mole percent oxygen, and 72.8% mole nitrogen. Right? The percentage conversion of methane is 90%. And the gas living reactor contain 8 mole carbon dioxide per mole carbon monoxide. Right? Okay, for this case is feed and product is mostly the gas phase. Also, we can conclude that the percent by mole. Like that. Also, this problem talk to you is by mole already. That's right, this by mole. Okay. The question is, please carry out the degree of freedom analysis on the process and then calculate molar composition. The molar composition of product, that's right, of methane, carbon dioxide, carbon monoxide, water, oxygen, and nitrogen. What is the composition in the product stream? That's right. Using the molecular species balance, atomic species balance, and Attain Operation balance. For the example, we will show you 3 techniques based on molecular species balance, atomic species balance, and Attain Operation. That's right, operation. Okay, the first step, we have to make a basis of calculation. For this case, we don't know the amount of flow rate, but you know the composition of feed rate. Okay, we can assume feed is 100 mole feed. Okay, we base it on 100 mole of the feed. Based on basis, you can calculate amount of methane in the feed, oxygen in the feed, nitrogen in the feed. That's how you can calculate. Okay, and then you draw the flow chart, right? You have a process and have input. Input is contain methane 7.8% is 0.078 mole methane per mole total, and 19.4 mole percent oxygen, that is 0.194 mole oxygen per mole total, and 72.8% mole in nitrogen. That means 0.728 mole nitrogen per mole total. Right. And also, we don't know the output of methane, we denote as N-methane, NCO, and NCO2, but we know from the problem that we know the ratio of CO2 per CO is 8 mole CO2 per mole CO, that you can express in terms of NCO2 equal to 8 NCO, 8 NCO, right? Okay, and water denoted as N water, oxygen denoted N oxygen, nitrogen denoted N nitrogen. Okay, and then you have to make the degree of freedom. For we have separate in 3 cases. based on molecular species balance. Molecular species balance. Okay, the first step, we have to count the number of unknown. This we have N methane, N CO, N water, N oxygen, N nitrogen. We have 1, 2, 3, 4, 5 unknown. We have 5 unknown. Through reaction, this reaction is independent. That's right. Total is 5 plus 2, that's 7 minus 6 independent molecular species balance. We have the 6 molecular species: methane 1, oxygen 2, carbon dioxide 3, water 4, oxygen 5, and carbon dioxide 6. That's right. We not include the nitrogen here because nitrogen is in there. That's right. Okay. We have 6 molecular species balance and 1 methane conversion. That's right. 1 methane conversion. You get 0 degree of freedom. Okay. You can use the molecular species balance to solve for the unknown. Okay. The next for atomic species balance. For atomic species balance, we have 5 unknown also. And we have 3 atomic species, right? Carbon, hydrogen, and oxygen. And 1 non-reactive molecular species balance, that is nitrogen. And 1 methane conversion, we have only 0 degree of freedom. You can solve unknown by atomic species balance also. And the last one based on Attain Operation. For this case, we have 5 unknown also, plus 2 independent reaction. That's right, we have 2 independent reaction, and minus 5 expression of NiC. That's right. We have the 5 components that in the reaction. That's right. Methane, oxygen, carbon monoxide, and water. That's in good reaction. And minus 1 non-reactive species, which is nitrogen. And then minus 1 methane conversion. You get 0 degree of freedom. Okay. That means that you can solve this problem by molecular species balance, or atomic species balance, or Attain Operation balance. Okay. For the next step, I will show you how to use this 3 technique. Okay. This 3 technique. Okay. The first step, because you know the information that's in 90% conversion of methane. 90% conversion of methane, that you can calculate amount of methane that remain or that unconverted. 90% conversion mean methane convert to the product is 90%. The methane feed is 0.078 multiplied by 100, you get methane. That's right. You get amount of methane in the feed. But the methane output is the amount of methane unconverted. That's right. Unconverted is 10% because it's convert 90%. Unconverted 10%, that means N methane equal to 0.1 multiplied by amount of methane in the feed. That's right. The amount of methane in the feed is 0.078 multiplied by 100. You get amount of methane output 0.10%, right? 0.1 multiplied by amount of methane in the feed. You get 0.78 mole of methane output. That's right. This is mole of methane output. Okay, the first step you can based on molecular species balance, and also for this case nitrogen. For this case, if you species balance, atomic balance, or Attain Operation, the nitrogen is the same. Why it is the same? Because the nitrogen is not incorporated in the reaction for this case. That means input equal to output for methane. That's right. There is no generation, there is no consumption, and for this process, it's steady state. For methane, input equal to output. Okay. The methane input, nitrogen input equal to output. Nitrogen input is 0.72. Okay. 0.728 multiplied by 100, you get amount of nitrogen. That is 72.8 mole nitrogen. For the information of conversion, you can calculate amount of methane output. And also based on the nitrogen is in there is no conversion, no generation, because it is not reactive component. Okay, input and output, and no accumulation, we call the steady state. Balance. You get already input equal to output. You get an input equal to 72.8 mole with equal to output for that case. Okay. Okay, the first we will consider the molecular species balance. If you recall the general equation like input minus output plus generation minus consumption equal to accumulation. Accumulation. Right? For this process, it is steady state process. There is no accumulation in the system or depletion in the system. No accumulation. If you consider water, if you consider water, water is product, and there is no water in the feed. That's right. No water in the feed. No water consumption because water is product. Okay. For this case, water there is no input. That's right. Output minus output plus generation equal to 0. That's right. For this case, output equal to generation for water. Okay. And then you can calculate G water in equation 1 mean the generation of water in equation 1 mean mole of water generated in reaction 1. Which is equal to C, that's right. C mean consumption. CO2 mean mole of oxygen consumed in the first reaction. From this reaction, you know that 1.5 mole oxygen consumed equal to 2 mole water generated on the chemical reaction. That's right. 1.5 mole O2 generate 2 mole water. You can relate the generation of water to consumption of oxygen from this case. Okay. From this case, you know, right, the generation of water equal to consumption of oxygen multiplied by the relationship based on reaction. That's 1.5 mole oxygen consumed equal to 2 mole water generated. And also for carbon monoxide balance. For CO balance, CO is product. There is no input also. There is no consumption. That means generation equal to output or output equal to generation. The output CO is NCO. NCO is the output of CO. NCO equal to generation. Okay. We denote that NCO equal to GCO from reaction 1 because CO generated from reaction 1. And also CO2 balance. No input, no consumption, but CO2 is product. Output equal to generation. Output equal to generation. Okay, for this case, you know the ratio of CO2 per CO, which you know, right? Is CO output equal to 8 NCO. That means output is NCO equal to generation of CO2 from the second reaction. You get this. You cannot solve now because this is unknown. Okay. The next one, we balance based on methane balance. Methane is the reactant, that is input methane, and output unreacted methane. No generation and methane consumption. No accumulation because it's listed. Okay. For this case, you get input equal to output plus consumption. You know methane input, 7.8 mole methane, equal to output. We calculate based on conversion already. So the output methane is 0.78 methane output. That's right. And methane consumption. Methane consumption come from two reactions. Methane consumption from first reaction. Methane consumption from the second reaction. That's right. Consumption from the first and the second. Okay. The methane consumption from the first reaction you can express as generation of CO, the same as water or CO or CO2. Right. Okay. It's equal to generation of CO multiplied by 1 mole CO generated equal to 1 mole methane consumed. This from the reaction 1. That's right. 1 mole methane consumed. 1 mole CO generated. That's right. Okay. So this is 1 mole CO generated. 1 mole methane consumed. This is the methane consumed expressed in terms of generation of CO. And also from the second reaction. From the second reaction, 1 mole methane consumed equal to 1 mole CO2 consumed generated. That's right. Okay, for this case, generation of CO2 from the second reaction is come from 1 mole CO2 generated equal to 1 mole CO methane consumed. That's right, methane consumed. Okay. Finally, you get 7.8 minus 0.78. You get 7.02 mole methane equal to TCO from equation 1 at TCO2 from equation 2. That's right, TCO from equation 2. And you know TCO1, you know TCO2 period reaction. That's right. Yes. TCO1 equal to NCO. TCO2 equal to NCO. You substitute NCO plus SNCO equal to 9 NCO. That's it, only one unknown. You can solve for NCO. That's right. You can solve for NCO. NCO equal to 7.02 divided by 9. You get 0.78 mole CO. That's right, mole CO. And then you know NCO, you can calculate NCO2 because NCO2 equal to SNCO. You get NCO2. Okay. Now you know NCO, you know NCO, you can calculate generation of CO from first reaction. That's right. Generation of CO from first reaction equal to NCO. And generation of CO2 from the second reaction is equal to SNCO. You can solve for this. You can solve for it. And then you make a water balance. The water is balanced from previously, sorry. It's water balance. Output equal to generation. Output equal to generation. In water, its output equal to water generation from the first reaction, water generation from the second reaction. From the first reaction, we can express in terms of generation of CO. That's right. Generation of CO means mole of CO generated. But you know, from the reaction, 1 mole CO generated equal to 2 mole water generated. Like this reaction. 1 mole CO generated equals 2 mole water generated. Okay. Equal to generation of CO2 from the second reaction. From the second reaction is also 1 mole CO2 generated is equal to 2 mole water generated. That's right. And then you substitute GCO1, this, GCO2, this, and then you can calculate in water. With the output water equal to 14 mole water. That's right. And then you make an oxygen balance. Oxygen balance is output equal to input minus consumption. As I showed you already. Because oxygen is reactant and also input. And convert oxygen is output and oxygen is reactant is consumed. This means output equal to input minus consumption. Okay, output is NO2. Input from the flow chart is 19.4 mole O2. That's why you have to know. Input oxygen 0.194 multiplied by 100 is equal to 19.4. This is the oxygen output. Oxygen output. And then minus CO2 consumption of oxygen from the first reaction is equal to generation of CO from reaction 1 multiplied by 1 mole multiplied by 1.5 mole oxygen consumed equal to 1 mole CO generated. That's right. Minus CO2 from equation 2. This is the consumption of oxygen from equation 2. That's right. It's the generation of CO2 from the second reaction multiplied by 2 mole oxygen consumed equal to 1 mole CO2 generation. You substitute GCO1 and GCO2, you can solve for NO2, which equal to 5.75 mole O2. Now you know output methane, carbon dioxide, water, oxygen, and nitrogen already. And finally, you get the total mole is 100.35 mole total. And then you can calculate mole fraction. For example, right, the fraction of water. The water is 5 water. Sorry. No, this is should be this oxygen. Okay, this mole oxygen. Oxygen is 5.75. The fraction is 5.75 divided by total. You get 5.7%. And also for the author, for methane is 0.78 divided by 100.35. Multiply by 100. You have to multiply by 100, you get percent. That's right. Sorry, you have to multiply by 100, you get percent for that case. Okay. If you have to multiply 100, you get percent. And this is for O2, not water. That's right. Okay. This is for O2. For example only. Okay. This will show you how to balance based on molecular species balance. And the next example, I will show you how to balance based on atomic species. Atomic, for this case, they include carbon, hydrogen, and oxygen. But you not necessarily to balance nitrogen because nitrogen is inert. Okay, the first step you balance on carbon balance. Please remember that for carbon balance, steady-state process for atomic balance, it is input equal to output. That's the input equal to output for the atomic balance. Okay, the first step we balance on carbon. Okay, carbon. If you look at the flow chart, carbon can input in methane, that's right, and output in methane, in CO, in CO2. That's right. We have one term input based on methane input, and three term output based on methane output, CO output, and CO2 output. That's right. Okay. And you can balance based on amount of methane input, amount of methane output, amount of CO output, amount of CO2 output. Okay. Carbon balance. The carbon balance, right? One carbon include in 1 mole methane. That means 1 mole methane include 1 carbon. But you feed methane is 7.8 mole methane. That's right. You can, okay. Mole methane cancel, you get this mole of carbon input. Okay, the next equal to mole carbon output. The carbon output in methane plus carbon output in CO plus carbon output in CO2. Okay, carbon output in methane. 1 mole methane include 1 mole carbon. The methane output is 0.78 mole methane output. This is also mole carbon. That's right. Plus mole of carbon in CO. That's right. In CO. Right? 1 mole CO include 1 mole carbon. And the mole of carbon output is NCO. That's right. Mole CO. Mole CO cancel. You get this. The unit is moles carbon. Okay. And carbon in CO2. Carbon in CO2. 1 mole CO2 include 1 mole carbon. And also CO2 output is NCO. That's right. Mole CO2. Mole CO2. You get mole carbon. Okay. For this case, you can solve for NCO. That is one unknown. NCO equal to 0.78 mole CO. And also you can solve for NCO2 because NCO2 equal to 8 NCO. Okay. From the carbon balance, you can solve NCO and NCO2. The next step, you balance based on hydrogen. From the flow chart, hydrogen. The hydrogen feed include only in methane. That's only one term in the feed. And output, hydrogen include in methane, include in water. There are 2 terms of hydrogen output. 1 term in methane input, and 2 terms output in methane and water. And then you can solve for that. Okay, that's right. For input, 1 mole methane include 4 mole hydrogen. And you feed methane is 7.8 mole methane. That's right. Mole methane cancel, you get mole hydrogen. And the first term of output is hydrogen in methane. 1 mole methane include 4 mole hydrogen. And the mole of methane output is 0.78 mole methane. And so you get mole hydrogen. And the second term is in of mole of water. 1 mole of water include 2 mole hydrogen. And mole of water output is NH2O. For this case, is NH2O is only one unknown. You can solve for NH2O or in water. It's 14 mole water output. That's right. The last one based on oxygen balance. Okay, you back to the flow chart. For oxygen input, we have only one term. The atomic oxygen included in molecular species oxygen. And output oxygen, we have 1, 2, 3, 4 terms. Oxygen in CO, oxygen in CO2, oxygen in water, and oxygen in molecule oxygen. Okay? And then you balance atomic balance on oxygen. For this case, you know 1 mole molecule oxygen includes 2 mole atomic oxygen, and the feed oxygen is 19.4 mole. Okay, and equal to output oxygen, which includes 4 terms. Oxygen in molecule oxygen, 1 mole molecule oxygen includes 2 mole atomic oxygen. Oxygen output is NO2. The second term is oxygen from CO. 1 mole CO includes 1 mole oxygen. And you know mole of CO output is 0.78 from previous balance. That's right. The third term on CO2. 1 mole CO2 includes 2 mole oxygen. And CO2 output is 6.24 mole CO2 from the balance. And the last term is from water. 1 mole water includes 1 mole oxygen. And you know water output is 14. And then you can solve for NO2. So you can compare atomic balance and molecular balance. You can see atomic balance is easier, it's better. Only 3 balance you get solve for unknown. Okay, the last technique is the Attain Operation. Okay, for this case, you recall the reaction. You have 2 reactions. And then you can write the balance based on Attain Operation. You can recall this equation. And I mean atom or molecule output, that's right, Ni is the number of mole or forest in the molecular forest, something like this. This Ni is the output, NiO is the input, plus summation nu I j Ci. That's right, nu I j is the stoichiometric coefficient. That's right. Stoichiometric coefficient of the species involved in the reaction. Ci is the extent of reaction. Okay, for this case, we have methane, oxygen, carbon, water, CO2. We have 1, 2, 3, 4, 5 equations that involve in the chemical reaction. Okay, you can express mole of methane in terms of extent of reaction. Methane output is N methane, which equal to 0.78. Equal to methane input. Methane input is 7.8 mole. That's right. And plus summation of nu I j Ci. Okay, the first reaction Vij V1 1. That's right. Nu of methane is -1 because methane is reactant. The stoichiometry is -1. Okay. -1 multiplied by C1. The second reaction is also -1 multiplied by C2. And then you get 7.02 mole equal to C1 plus C2. This is for the methane. And then for carbon output, carbon monoxide, mole of carbon monoxide output equal to input. Input is 0, that's right, plus summation nu I j Ci. For this case, carbon involved in the first reaction only. That means carbon is product, is +1. +1 multiplied by C1. There is no the second reaction. Okay, for this case, you go for second term. And the next term is CO2. CO2 output is NCO2, which equal to SNCO. Equal to output, equal to input. There is no CO2 input. That's right. It's 0. And then plus CO2 is +1. That's right. +1 multiplied by C2. You get it. And water. NH2 is water output equal to water input, but there is no input water. Plus nu Ij for the first reaction. For water is +2. That's right. +2 multiplied by C1. For the second reaction is +2 multiplied by C2. Yes. Okay, the next term is oxygen. Oxygen output equal to oxygen input. Oxygen input is 19.4 plus Cij. For the first reaction, that's like nu Ij. The first reaction is nu Ij. The stoichiometric coefficient of oxygen is minus 1.5. That's right. 3/2 or minus 1.5 multiplied by C1. For the second reaction, it's minus 2. Minus 2 is C2. That's right. Minus 2 is C2. Okay. We have 1, 2, 3, 4, 5 reaction. If you see that for this case NCO equal to C1, you can substitute C1. That's right. And also NCO2 equal to NCO equal to C2. You substitute it, you get this reaction. That's right. 7.02 equal to NCO plus 8 NCO is only one unknown. You can solve for NCO. That's right. If you know NCO, you can solve for C1 and C2. That's right. You substitute C1, C2, you know N water and N oxygen. That is the same answer. So you calculate like for this. You get the same answer from the atomic balance or molecular balance, something like this. It shows you why we can solve by three technique. But mostly if a simple reaction or one reaction, you can use molecular balance. If it's complex reaction, is Attain Operation is people or atomic balance. Right? And for the reversible reaction is Attain Operation is preferred. But for all this, you can use the three technique. But if you like to use that, but for easy way, if the simple reaction, okay, molecular balance can be used. That's right. For complex reaction, okay, multiple reaction, something like this, the atomic balance is preferred. And also if reversible reaction, Attain Operation is preferred, something like that. Okay. The next, we talk about the product separation and recycle. If we have some recycle, that's right. If we have recycle, we have two terms that are very important to talk about overall conversion and single part conversion. The overall conversion is defined as the reactant input to the process, and reactant output from the process, divided by reactant input to the process. For this example, right? If you would like to calculate overall conversion from A to B, that's right, the conversion of A input to the process is 75 mole A per minute, and output is 75 mole B per minute. That's right, there is no A output. That means there is no A output for this case. Okay, and then you can calculate overall conversion. That's right. For 100 mole A per minute, there is no input to the process. There is input to the reactor. That's right. 25 mole A per minute. This output from the reactor, not output from the process. 75 mole B per minute is the output from the reactor. Okay, the overall process is like this. This is the overall process. Input, output. If reactor, input to reactor, output to reactor. That you have to determine the conversion for the overall. You have to utilize the overall input, output from the overall. For single part conversion, you have to calculate based on input, output of the reactor. For this case, the overall conversion is input mole of A is 75 mole A per minute in minus 0 mole per minute of A output divided by input, you get 100% conversion for this case. And single part conversion for this case, you know, like the input is 100 mole per minute A. Output is 25 mole A per minute divided by 100 multiplied by 100, you get 75 mole percent conversion for this case. That's right, for this case. Okay, I think it's clear. For example, like it, we consider a dehydrogenation of propane. Dehydrogenation of propane. Propane from this reaction to produce propylene with a catalytic reaction. For the catalytic reaction, we have some catalytic to accelerate the reaction. In this case, we have 3 chemical and 1 catalytic. It may be solid catalytic or solution catalytic. For this case, we consider only the chemical reaction, not consider the catalytic. Okay, the propane, that's right, hydrogenation by catalytic reaction to produce propylene and water, or propylene and hydrogen. This equation is balanced already. That's right, it's balanced already. The process is designed for 95% overall conversion. This is an overall conversion. Convert feed to the process, output of the process. That's right, of the propane. The reaction product are separate into stream. That's right. The product into stream, the first is the product and the second is recycle. That's right. The first contain hydrogen, propylene is hydrogen, propylene, and 0.555% of propane that leave the reactor. Taken off as product. That's right. For this case, what does it mean? The output is include the propane, propylene, and hydrogen. But propane is 0.555% of propane leave the reactor. This means 0.55% of propane from reactor. That's right, for this case. Okay. The second stream is the recycle, which contains the balance of the unreacted propane, balance of unreacted propane. That's right. And 5% of propylene in the first stream. 5% of propylene in the first stream. That means the propylene from in recycle is the 5% of propylene in the product stream. That's right, in the product stream. Okay. The question is calculate the composition of the product. Calculate the fraction of N6, N7, N8, something like this. That's right. And the ratio of mole recycle per mole phase feed. The ratio of mole recycle is to the phase feed to the reactor. Sorry, phase feed is the phase feed to the process and single part conversion. Okay. And after you consider the problem statement, and then you can make the basis. For this case, you make a basis is 100 feet mole. That's right. Is mole propane. For this case, you don't know the amount, you don't know the flow rate, and you don't know the composition for each case. Okay, the basic simple like we assume like 100 mole phase feed. For this case, we calculate based on 100 mole phase feed. Okay, and then you draw the flow chart. The phase feed you know already. Okay, the reactor. That's right. Feed propane to reactor we denote N1. Feed propylene to reactor is N2. The propylene is feed from the recycle. That's right, from the recycle. And the propane out of the reactor is N3. Propylene out of the reactor is N4. Hydrogen is N5. Propane as product is N6. Propylene as product is N7. Hydrogen as product in N8. And another, we have one information, like the mole of propane output is 0.555% of propane phase feed to the separator. That's right. Okay, V is equal to 0.55% of N3. And also, the recycle, we denote N9 for mole propane and N10 for mole propylene. And right, the propylene from the problem statement is 5% of N7. That's right, 5%. Again, you finish the basis and then you finish the flow chart already. And then you draw the degree of freedom analysis. Okay, for this case, if you consider the overall, you count number of unknown for overall. That's right. We have N6, N7, N8. We have 3 unknown. That's right. We have 3 unknown. If you balance based on atomic balance, it's only 2 atomic balance is carbon and hydrogen. And we have no the overall conversion is 95%. And you get 0 degree of freedom. You can solve N6, N7, N8 from the overall system. That's right. And then you degree of freedom analysis based on recycle phase feed mixer for this case. We have N1, N2, N9, N7. We have 4 unknown. That's right. We have 4 unknown. If you balance based on the chemical species, we have only propane and propylene. We have 2 balance equation. And we get 4 minus 2 is 2 degree of freedom. We cannot solve for N9, N10, N1, N2 from recycle phase feed mixing. Okay, you cannot do this. The next step, you consider reactor. For reactor, We have N1, N2, N3, N4, N5. 5 unknown. That's right. 5 unknown. N1, 2, N5. And if you consider the atomic balance, we have 2 atomic balance, carbon, hydrogen, and also 3 degrees of freedom. You cannot solve for N1, 2, N5 for this case. And okay, the next step, you check separator. The separator we have N3, N4, N5, 1, 2, 3, 4, 5, 6, 7, 8. That's right. Yes. But now you know 6, 7, 8 already from the overall balance. That's right. Now we have 1, 2, 3, 4, 5, 5 unknown. That's right. N3, N4, N5, N9, N10. N6, N7, N8 you know already from the overall balance. The first step you have to overall balance. That's right. Okay. The next step we don't know now. Okay, we have checked the last one, separator, 5 unknown. That's right. And if you balance based on molecule balance, we have 3 molecules, propane, propylene, hydrogen. And also we have 2 information, right? N6 equal to 0.55% N3 or 0.00555 N3 and N10 equal to 0.05 N7, right? From the flowchart, you know this and you know this. Okay. 5 unknown, 3 balance, 5 minus 3 balance minus 2 in the information, you get 0 degree of freedom. Okay. And then you can solve for N3, N4, N5, N9, N10. That means you can conclude that the first step you have to overall balance. You can solve for N6 to N, yes, and then you run on separator. You can run your separator, N3, N4, N5, N9, N10, and then you can solve another balance like N1, 2. That's right, N1, N2. That's right, N9, N10. You know already. You can solve with the third step like this. Third step like this, or you can solve for the third step by reactor. It's up to you. That's right. If you balance on phase, N1, N2. If you balance on reactor, also N1, N2. Also, for this case, okay, we have 3 steps. Right? The first step, overall balance. The second step, separator balance, and the last step, recycle phase fit mixture point or reactor. Okay. Okay, for this case, the step to solve the unknown. Okay. The first step, we consider the information. The information, the first that we know before overall balance, we know the overall conversion is 95% overall conversion of propane. What does it mean? It's 95% propane convert and 5% propane unconvert. That's right. That means you can calculate N6. N6 is propane output. That's right. Propane output is the propane unconvert. It equal to 0.05 because it's 5% multiplied by the feed propane. If propane is 100, you get 5 mole propane is unconverted equal to N6. N6. Okay. And then you start the overall balance. For the overall balance, for this case, we based on atomic balance. Okay, the first we overall carbon balance. Atomic balance input equal to output. For carbon balance, for overall, that's right, carbon input in propane, output propane and propylene. 1 term input and 2 term output is overall. That's right. Okay. For input, 1 mole propane includes 3 mole carbon. That's right. And feed propane is 100 mole propane. You can sell mole propane. This mole of carbon equal to output. Output we have propane, carbon in propane and propylene. Okay, the first you consider, right? 1 mole propane includes 3 mole carbon, and right, the output of propane is N6. That's right. Mole propane. You get mole carbon. N6 already from previous balance. That's right. And the second term based on propylene. That's right. 1 mole propylene includes 3 mole carbon. That's right. 1 mole propylene includes 3 mole carbon. And the mole propylene output is N7. That's right. N7. Mole propylene. Mole propylene is mole carbon. That's right. Right, right hand side, left hand side is the same unit. That's right. And also, right, the addition is also the same unit. This mole carbon, this mole carbon is the same. Okay, you substitute N6, you can solve for N7. Now you know N6, N7, and then you make like the hydrogen balance. The hydrogen balance you can consider the flow chart. Hydrogen input is one term in propane. Output is three terms. Got output in propane, output in propylene, and output in hydrogen. That's right. Okay. First term input. That's right. The first term input. You know, 1 mole propane includes 8 mole hydrogen. That's right. The propane input is 100. We get this term. And output we get 3 terms. Output in propane. 1 mole propane includes 8 mole hydrogen multiplied by propane output. Okay. The second term in propylene, you know, right? 1 mole propylene includes 6 mole hydrogen, and propylene output is N7. And the last term in molecule hydrogen, you know, right? 1 mole molecule hydrogen includes 2 mole atomic hydrogen, and hydrogen output is N7. Okay. But now you know N7, N6 already. You substitute N7 and N6, you can solve for N8. You get N8 equal to 95 mole hydrogen with the hydrogen output. Right, the hydrogen output. Okay, for this case, you know N6, N7, N8. You know the product composition, and then you know right that propane is N6, 5 mole propane, N7 is 95 mole propylene, and 95 mole hydrogen. That's right. That's right. The summation of this is the total mole of product, and then you divide this 5 by total, you get fraction, and you multiply by 100, you get mole percent. Something you can calculate the composition of product. That's right. Okay, and moreover, that's right. In this case, you know, right, the N6 is equal to 0.0055 N3. You can solve for N3 also. That's right. N6 equal to 0.00555 N3, and then you substitute N6, you get N3, and also N10. N10 is 5%, N7 is 0.05 N7. That's right. You get N10. From the information, you can solve for N3 and N10 also. Okay. The next step, you balance based on separator. That's right, the separation. If you balance the total mole of separation, it's separation. That's right. If you balance based on propane or propylene, first step you balance on the propane balance. Okay. Propane balance, propane input the separator is N3, output is N6 and N9. That's right. You know N3, you know N6, you can solve for N9. That's right. You know N3 from here, and you know N6 from this. Okay. From the propane balance, input is N3, output is N6 plus N9. This balance about the separation. N3, you know N6, you know, and then you solve for N9. That's right. You know N9, you know N10 already. That's right. You know N6. Okay. And then you can solve for propylene. That's right, propylene. From the propylene balance, N4 equal to N7 plus N10. You know N7, you know N10, you can solve for N4. And then hydrogen balance, N5 equal to N8. You can solve for N5. Okay. But this case I did not do for that because it's not necessary because the question didn't talk about this. The next step, we balance based on mixing point. The mixing point, we balance our propane on the mixing point. The mixing point propane balance input have two stream, right? 100 propane input plus 100 plus N9 propane in the recycle equal to N1. You know N9, you can solve for N1. That's right. And then you can balance on propylene. N10 equal to N2. You can solve for N2. Yes, okay, there. You can solve for N1. And then the recycle ratio, the question for the recycle ratio is the recycle amount is N9 plus N10. You know N9, you N10. That's right. And then you divide this by 100 mole fresh feed. You can calculate the mole ratio of recycle and fresh feed. And single part conversion. The single part conversion based on the propane convert. You have to calculate propane feed to the reactor is N1. Propane output of the reactor is NT. That means N1 minus NT divided by N1 multiplied by 100. You know N1 NT already. You can solve for that. You can solve for that. Okay, you stop for this example and we continue for the next lecture. We talk about the purging. The purging. Okay. See you for the next.